So my name is Trevor Plint, and I'm a PhD candidate in the Faculty of Chemical Engineering and Applied Chemistry at the University of Toronto. A combined screening approach for novel materials for organic electronic devices. We've been over some of the potential advantages. They have the potential to be light and flexible, and they can be cheap to process. Their efficiency hasn't, and as we've seen, likely won't surpass that of silicon. We're still fighting the cost variable for these carbon-based organic electronic materials for photovoltaics. And I think the central bugbear is that we can't design carbon-based materials with arbitrary electronic properties. So what are we looking for? So we have to do this the hard way. We have to go by material screening. We're looking for things like charge carrier mobilities that match as well with the acceptor, usually some sort of fullerene, processability, absorption in the right part of the solar spectrum, and good exciton dynamics. But synthetically, what does this entail for the synthetic chemists? Basically, it means we start with a motif and we try variants, basically, and try and find out what works and what doesn't, because it's not always immediately obvious a priori what it's going to do. So, as my supervisor was just outlining, we started with a metal phthalocyanine sort of motif. We made a whole bunch of variants on it, and then you want to go off and try and make OPVs. But there are difficulties associated with this because OPV optimization requires a lot of different steps. You have to go after the thickness. You want to look at the morphological characterization. Sometimes they're going to crystallize in unpredictable ways. You want to get into charge transport measurement and then start looking at interfaces. And overall OPV performance is very sensitive to minor perturbations. For example, you run into batch-to-batch variation problems, which can cast sort of questions on what are these efficiencies and like what are they really. And it can be hard to diagnose changes based on the electrical outputs. If your VOC changes, how do you work backwards to figure out what that means about your film? So the question is, how can we optimize OPV material selection without actually making any OPVs? So that's what I've tried to do is by making bilayer OLEDs. And the idea is that a material that makes a good bilayer OLED might also make a good OPV. So architecturally, here's what our structure is for an OLED. Here's a picture of them. We're making them from these phthalocyanine motifs. You push in electrons and holes, and you get light spat out. That's one of our pixels lighting up, bright green. So energetically, we're giving some energy to an electron on one side, causing a vacancy, a hole to form on the other, and when an electron falls into a hole, they annihilate and they boot off light. Now, if we switch from an OLED to a planar bilayer OPV, we're effectively doing the same thing in reverse. We're creating a bound exciton, which, if it migrates to the interface, dissociates, and we get a flow of electrons in one direction, then a sort of flow of holes going in the opposite direction. So there are a lot of similarities between a bilayer OLED and a bilayer OPV, materialistically. So here are results for our phthalocyanine derivatives in terms of the OLEDs. Let's see if I got a laser here. Okay, this is the luminance in a logarithmic scale, so this is the brightness here. This is a baseline material here that we just use as a point of comparison. And what we found was that the F10 silicon, so that's the 2-pentafluorophenoxy silicon phthalocyanine, does really, really well. Chloroaluminum also does really, really well. And then dichlorogermanium phthalocyanine, dichlorosilicon phthalocyanine, and chlorotin phthalocyanine, kind of threw in there, all have moderate to poor OLED results. So how does this map onto our OPV devices? We actually went off and made some OPVs of these things. And as it turns out, chloroaluminum works quite well. F10 silicon has an increased VOC, which in practice it means is very good. And chlorosilicon and chlorogermanium is kind of this little dot down here. So by and large, it maps on. So we can use OLEDs, which are robust, they're very quick. You can, because you're pushing current into them, they're a lot less sensitive to all these parameters that makes testing an OPV a bit of a headache. So effectively, what we're finding is that good bilayer OPV materials are also going to be good bilayer OLED materials. So we can use an OLED as a screening tool. It gives us an additional view on compounds to determine whether they might be of interest. And the synthetic chemists are basically always going to have the upper hand when it comes to the materials-device equilibrium. They can always make materials faster than we can optimize devices. So until we can design materials with an arbitrary set of electronic, optical, and morphological properties, we're kind of stuck with traditional screening. And the faster we can hit that economic sweet spot for these, whoops, that's mine, thank you. The sooner we all get rich. So thank you, and I'll be happy to take some questions.